lights in the trees is the same that stirs in me. And the best things have always been free. I can taste the dust I'm of, taste the hope and loss and love of the countless who lived before me. So let's raise our noses high, let's toast to this new life and the ecstasy found in each breath. Let's dance in the light of dawn while the curtain remains drawn in this brief intermission between death. We're alive, magnificent in this world where each sun rises a symphony, and you are a work of art. Let's whistle while we walk, don't heed the tickle talk of that mechanical bandit clock. You're burdened down by time and dive deep in another's eyes where the hours melt like waves on the rise. We're alive, magnificent in this world, where each step you take makes history. So join in and play your part, and each passing smile's an eternity. Who knows what it could start? Where each creature sings in harmony. Let's join in with all our hearts. We're alive. Than I could ever dream, and my love, you're the very best part. And I don't think I'm ready for what's coming, but maybe we'll just blame it on the timing. So baby, what can I say if it's too little too late for you? She's got a kind of way of acting. She's always saying what she's thinking, and I don't wanna be losing out on you. We play these dangerous games, 'cause I don't really know how to feel, how to say that I'm losing my head to you. Now we're drinking, and I don't think I'm ready for what's coming, but maybe we'll just bear it on the timing. So baby, what can I say if it's too little too late for you? She's got a kind of way of acting. She's always saying what she's thinking, and I don't wanna be losing out on you. She's got a kind of way of acting. She's always saying what she's thinking, and I don't wanna be losing out on you. She's always saying what she's thinking, and I don't wanna be losing out on you. She's got a kind of way of acting. She's always saying what she's thinking, and I don't wanna be losing out on you. Sometimes worlds collide, love ignites, or big dreams die. Either way, we try our whole life, try to be someone with the whole world up against us. Have you ever wanted to be somebody else? Or maybe you're going through some kind of hell. See, I got this belief that if your heart is still beating, it's a good day to be alive. It's a good day. It's a good day to be alive. You know, nobody lives forever, right? So right now, I'm just gonna let it all hang out. Only got one life to be myself. Blue skies and my inhibitions in the wind. These are old shoes. I've got a brand new kick to them. Make me wanna dance all night. Yeah, it kinda feels like anything could happen. It's a good day to be alive. Just one of those days, gravity can't hold me down. Just one of those nights, we're gonna sing a little too loud. I see life, champagne in the sky, and stars born on the ground. Just take a look around. I like shaking up tradition. I don't fit into any mold. Still, I'm no exception. I've been high and I've been low. But see, I got this belief that if my heart is still beating, it's a good day to be alive. It's a good day. It's a good day to be alive. You know, nobody lives forever, right? So right now, I'm just gonna let it all hang out.
Okay. Welcome, everybody, to the last tutorial session of the day. This talk will be on attention in deep learning, a powerful and important architecture, I think. And it's going to be presented by Alex Smola and Aston Zhang, both from Amazon Web Services.
Okay, so thanks for coming in here. And so I hope that in the end you'll take something away about attention. So who thinks that the average attention span of the human is longer than that of a goldfish? Actually, it turns out not quite. So goldfish beat humans by 1 or 2 seconds. We'll get to that later. But okay, so nonetheless, attention is kind of important. And, well, wow, there's a lot of echo. So there's one important URL you probably want to remember. If you go to bit.ly and you type in 2 capital R 10 lowercase h capital T lowercase u, you'll get all the slides. Or you look at my Twitter feed or anywhere else. Okay, so let's get started. Given that people are still streaming in, let's start with something very easy, right? So a bit of biology. So I guess everybody knows what that is. That's a cross-section of an eye. And one very important thing about this eye is that there's this thing called the fovea. So the fovea is the part where lots of essentially pixels are, if you want to put it in computer speak. In other words, where your sensor has very high quality. And, okay, so, well, what does this have to do with this tutorial? Well, suppose you need to make those slides, right? And you're feeling kind of a little bit tired, and you need to look through all those papers, right? And to make sure that, you're up to date with the latest papers and everything. Well, then maybe because you're feeling a little bit tired, you should focus your attention weighting onto, well, that little cup of coffee. And so what happens is basically you're now using a significant amount of your sensors, of your receptive field, for that cup of coffee, and then, well, you drink the coffee, and then, you feel a little bit strengthened by it, and, well, then you can attend to the papers and work through them one by one. In other words, you don't necessarily perceive the world uniformly, in the sense that you're not investing the same amount of information processing capacity uniformly on everything, but you focus on specific things. So, for instance, I hope that during this tutorial that Aston Zhang and I are presenting, you will focus a lot of your attention on what we're saying as opposed to maybe what's going on your Facebook. Right. So, okay, that sounds silly. Let's look at why nature has invented stuff like this. And this is, full disclaimer, the glib, stupid computer scientist's version of it. But basically, if you think about it, attention in animals does a number of things. One of them is resource saving. So what that means is that you only really need the sensors where relevant bits of information are. So you only need to focus with your fovea on the pieces there for high resolution. Actually, it turns out your peripheral vision is really good for movement, so there's a different type of attention there. And the other thing then is you only need to do the computation there. That actually matters quite a bit because, well, animals are quite energy constrained. They're very energy efficient. And if I can avoid doing a lot of processing in areas that I don't really care about that much, well, I can save my energy for something else, like thinking harder, being smarter, whatever. The other nice thing is that this attention allows you to manipulate a variable state relatively efficiently. Okay, so let's look at that cute chicklet on the lower right, and that is trying to eat some yellow grains. And this chicklet probably has learned at some point how to eat a grain. And so now, in order to eat, in this case, probably something like a dozen pieces of grain, it executes the eat grain subroutine for every one of those grains, and then it moves its attention to something else, executes this routine again, and so on. So in other words, that chicklet didn't have to learn the eat grain routine for 1 or 2 or 3 or 4 and 5 pieces of grains, but it just had to learn that subroutine, and now it could iterate and apply it. So this makes things a lot more modular, and in machine learning parlance, this means also that you have a much more non-parametric model. That's really the key idea there. So the question is, of course, can we steal those ideas and apply them to machine learning? And if the past 5-6 years are anything to go by, the answer is very clearly and resoundingly yes. So I said the past 5-6 years. Actually turns out that, if you will, attention is an idea that's at least 55 years old, if not older. So I'm going to start with something that you may have heard of, namely the Watson-Nadara estimator from statistics. And then I'll look at pooling, so single objects and hierarchical structures, iterative pooling, so this will get us to question answering for images and text in memory networks, and then iterative pooling and generation. So in this case, we don't just iterate over our state, but we emit things at every step, and that gives you machine translation, pointer networks, and other things. And then, of course, because attention is good, multiple pieces of attention are even better, and that'll get us to transformers and BERT. And then we'll conclude with a few pointers to where things currently are at. In this context, basically lightweight, structured, sparse models. And in the end, we'll talk a little bit about some resources to help you get started. Okay. So let's start with something very, very old. So Geoff Watson and Elisabeth Nadaraia, independently in 1964, had an idea of how to solve the following regression problem, or something like this. So if you look at that, it's basically, a sine function with a little bit of noise added, and I observe those 5 points. So in other words, I have some data, xi, and labels yi, and I want to estimate y at a new location x. Right? So sounds kind of obvious, right? So what I could do is I could design the world's dumbest estimator. Well, maybe not the very dumbest, but pretty close to that. And what I could do is I could say, well, let's just average over all the labels that I've seen. So let's assume there's a regression problem. Otherwise, it gets a little bit more interesting. But what I can just do is I can say, well, y is the average over all the yi's. In other words, completely ignore the x's and just use the yi's and the average. And if you do that, well, if you look at the graph on the right-hand side, well, you get the constant function. And that sounds dumb, but it's actually not that bad quite often. Of course, you can do better. And so the idea, independently proposed by Geoff Watson and Elisabeth Nadaraia in 1964, was, well, let's actually weigh those labels according to the location. In other words, let's have some weighting function alpha that depends on x and xi and yi, and then use that to come up with a good estimate like a regression. And so if we unpack this and rename things in the parlance of how people now do that for, attention in deep learning, then this function alpha takes 2 arguments. It takes a query, namely x. This is the location where I want to perform my regression. Have a key xi, so that's the set of covariates that I'm using. And I'm basically looking at the distance between x and xi. And then I have some value yi. In some cases, sometimes the key and the value will be the same later on, and sometimes even the query will be the same or related, and we'll call that self-attention and so on. But for now, let's just assume that I have a query, a key, and a value. And this is, at its very heart, the attention mechanism. So if you remember nothing else from the entire tutorial than that, you've already made big progress. Okay, so now, of course, let's look at what those weighting functions might look like. For instance, I could take a Gaussian. So I could take the squared distance between, key and query, so between x and xi, e to the minus 1/2 that, or maybe some other coefficient up front, and I get those nice little bumps there. And you can already see that this isn't quite the answer yet, because those weights may sum up to more than 1 or less than 1. Right? So that's not quite the solution. What you want is that your weights always sum up to 1, such that you get the weighted average, and there's nothing easier to do that than to normalize them. And this is, by default, actually the normalization approach that people use. So what you just do is you sum over, all the k of xj and x, and use that as a normalization factor for the k of xi and x. And if you do that, you get that. So the orange function is now my regression estimate, and the green function, well, that's the original ground truth, but I don't really have that at my disposal. All I have is just those 5 dots. And given that, it's actually not too bad. Because after all, there's no way our poor regression estimator has any way of knowing that, for instance, as x becomes more positive, the green function decreases again. As a matter of fact, if anything is to go by, if you look at the 2 stars on the right, you might think that the function would keep on increasing. So that's about as good as it gets. Okay. So this is attention in the style of, 1964. Okay, so you're wondering, you've come to a deep learning tutorial, right? And I'm telling you really old statistics things, right? So, why bother about something that's 55 years old? Most of us are less than that old, right? So, one of the really nice properties about this really ancient algorithm is that it's consistent. So what that means is, given enough data, this algorithm actually does converge to the optimal solution, right? And for many deep networks, proving that is actually a lot of work. And in many cases, it might not be possible if I have a neural network with a fixed number of weights. Let's say I take a ResNet, like say ResNet 50. Then proving that this will converge to the optimal classifier. If I take data like from ImageNet, but an infinite amount of that, well, that's probably not going to happen. This ancient algorithm actually beats it in that property. I mean, of course, I'm not arguing that you should use the Watson-Nadari estimator for image classification, but if you look at its theoretical properties and what's known about it, it's pretty good. The other nice thing is that, it doesn't really have any free parameters, right? So I just take the data, I weigh it, and presto, I have my regression estimator. So what can we learn about it for today? Well, of course, we can make this deep. So I might want to learn a weighting function, and I might want to replace, therefore, averaging pooling operations by weighted pooling. And this is kind of the marching orders for how to use attention in its simplest form, namely for pooling. Okay, so now that everybody's in the room, let's start with the fun stuff, right? Pooling. So there's this algorithm called deep sets. And essentially, so by Mansilza here and others, so essentially what we did in this algorithm is we asked the question, if I want to define a function on a set, so with that it means that it needs to be permutation invariant. In other words, if I give you, f of the set, or if I go and permute the elements of the set, I always want to get the same answer. And if you apply this constraint, so this invariance, and ask, what's the general class of functions that I could possibly get? Then it turns out that with some minor footnotes, essentially this function can be written as some nonlinearity of the sum of some other nonlinearity of each element of the set applied individually. In other words, take every element from the set X, apply phi to it, sum it up, apply rho to it. And this works really beautifully, and you can use it for point clouds, or set extension, or redshift for galaxy, or text retrieval, or tagging, and so on, or graphs, right? Basically, anywhere where you have permutation invariance, you can immediately apply this hammer and say, okay, this drastically reduces my function class, the things that I need to learn, and I just need to learn those two nonlinearities, and I'm done. So, for instance, you can use that to detect outliers in sets of images, and so these are some pictures, and basically we inserted, an outlier in each of those, and we had the network determine what the outlier might be, and in a fair number of cases actually gets it right. Doesn't get it right in the middle, but try for yourself to see whether you can easily identify that. And, well, so in the middle, the idea was, double chin and wavy hair, and if you don't have that, well, it's not so good, but okay, try by yourself. So it's actually quite surprising that he gets this right. Okay, so this is a very simple averaging pooling operation. So drum roll, please. Of course, there's an attention version of this. So last year, I think at ICLEA, Ilse, Tomczak, and Welling used the same idea and extended it with attention weighting. So the problem that they tried to solve is one for which attention weighting is actually really quite useful, namely multiple instance learning. So imagine you want to do drug discovery, and so you inject your your lab rat or whatever with a cocktail of drugs, right? And you then check whether the drug, that lab rat gets better or worse. And if it does, and assuming that those drugs don't interact with each other, well, you can therefore conclude that maybe there was one drug in that cocktail that actually made the lab rat healthy again. Okay, sounds good. The problem is you don't know which one it is. And of course you can go and, do interval halving and all of that. But then actually doing this properly and synthesizing, the corresponding cocktails and all of that is quite labor intensive, so maybe you can do better otherwise. This is called the multiple instance problem. Another application, like a model application, is if you have a big key ring with many, many keys on it, and the key ring opens the door if one of the keys opens it, but I'm not going to tell you which one. And your goal is to find out whether, a certain key ring and thus a certain key opens the door. So one way of doing this a little bit better is to learn an attention function which helps us in this context to identify which of the keys or the drugs or whatever other things might be relevant through attention weighting. So I have some function alpha of w and x. W can either be learned or it can be, query dependent, maybe depending on a particular lock. X is the key of, for instance, the key of the drug, and then phi of x would be the value that you aggregate. Popular choice for an attention function is e to the w transposed tang of vx, but there are lots of other choices that you could pick. And so it turns out that this works quite beautifully. As a matter of fact, if it didn't, probably we wouldn't have this paper. So in a toy experiment, what they did is they looked at, can we detect nines in a bag of digits? Because essentially the property was, does it contain a 9 or not? And guess what? It's pretty good at detecting nines. In this case, there are 4 nines, and they all get about equal weight. A rather less frivolous application, this would be this one there. So deep sets for, well, cancer. So suppose I have a tissue sample like the one on the left, and my goal is to identify whether it has any cancerous cells in there. So a good strategy is first to identify what the cells themselves are, and it turns out that there are some subroutines that will very nicely allow me to pull out those windowed cell nuclei. So it's basically, looking at all the locations where those cells are, putting, a little window around it. So now I have turned this image into a multi-instance problem where effectively I have a long list of pictures of little nuclei. And the second image from the right, this is a picture of all the cancerous cells. Right? Of course, I don't know that. I just know that, well, okay, this person has cancer. Right? But what I can do is I can now learn a set kernel, sorry, a deep sets problem with attention weighting, and I can look at the attention weights that I'm getting. And it turns out that the attention weights are exactly what I would have expected. So, there you go. And then they show that this actually works very well. Okay. So this is about as simple an application as you can think of in the context of attentions and sets. Right? So anything that we'll do from now on, we'll just repeat this pattern. The only difference is that we'll make it a little bit more complicated. So to recap, what we're doing is we are basically pooling with an attention weight. And then we have some embeddings, so phi of x. And this is what allows us to then come up with some conclusion. Okay. Now, here's a slightly more interesting application. So suppose I want to classify documents, right? So what I could do is I could, take my trusty word2vec embedding, or maybe I use some, bag of words embedding, right? So just indicators like Salton and McGill, or I can use a GRU or an LSTM, and I basically take every word as we go along and I embed it, and then in the end I get those embedding vectors out. For instance, for the tutorial is awesome, and of course the tutorial is pretty boring for that regard, but awesome is really the thing you care about. And then, you're happy. And so this is, what people typically would do for a bag of words or a bag of embeddings to classify, for instance, sentiment. Well, the trouble is that if this obnoxious Alex comes into play, like Alex is obnoxious, but the tutorial is awesome, then things go badly wrong, right? Because the Alex is obnoxious part, especially the obnoxious piece, and the but have negative connotations, and they will completely swamp the rest. I mean, obviously you're not here for the Alex, but you're here for the tutorial. So we all know that this should be still a positive sentiment, but our deep network doesn't know. So the goal would be to ignore this. And of course, we already know what the answer has to be, namely, we can use attention weighting. So it's exactly what Wang et al. Did in 2016. Actually, they didn't use a bidirectional LSTM or a GRU in the bottom. They just use a unidirectional one, but it doesn't really matter for this. And so what you can do is you can just replace the pooling over the embeddings by an attention-weighted pooling over the embeddings, and this works better. Okay. So what you probably would have noticed already now is that actually those references don't necessarily come in chronological order. As a matter of fact, we'll get to a rather complex model later on, namely machine translation, which was sort of the condensation point or germination point of a lot of this attention work. And that actually came fairly early on, and then people afterwards stripped away pieces and simplified it. So this presentation I'm giving you right now is conceptually from simple to complicated, but actually people came up with the really difficult things first and then they simplified it later. So it's kind of funny. Now, okay, so we have something, how to deal with the obnoxious Alex. But what about that? So let's look at these two reviews, right? So these are Yelp reviews, and one of them, for instance, where, ground truth is that this person pretty much liked the restaurant, goes like this. Pork belly equals delicious scallops. I don't even like scallops. And these were amazing. Fun and tasty cocktails. Next time in Phoenix, I will go back here. Highly recommended. Or another one, which, wasn't very good. Terrible value. Order pasta entree. $16.95, good taste, but size was an appetizer size. No salad, no bread, no vegetable. This was and tasty cocktails, our second visit. I will not go back. So if you look at the review on the right-hand side, if you just, balance positive versus negative aspects, you'd think it's kind of level, right? I mean, the food actually was pretty good. The cocktails were tasty. But then, and this is our second visit, right? So there are a lot of good things about this place. Turns out, it's really overpriced and he's not going to be back. So the first and the last sentence are really the things that matter. Everything in between is just fluff to, show that he's thought of different aspects. But he really pants this place and he hates it. So what that means is you would really want to be able to weigh not just words within a sentence, but also sentences to trade off things in terms of, what matters and doesn't. And if you look at the colors, the different hues of red tell you how you can go or how you should probably weigh the various sentences, whereas the different shades of blue will tell you how you should weigh the words within the sentence. So now you have attention within words of a sentence and within sentences. And so if you compare to this picture here, now we'll see the full story. Namely, you can have attention weighting within a sentence. You pull that together. And then you get attention weighting between sentences, and you pull that together again. And guess what? That works. And yeah, that's what we did. And you get pretty good models. I mean, nowadays, rather than a GRU, you would probably go and use something like BERT, and it might work an epsilon better. So if you have an undergrad, that's probably a cool project to get them started on. Right. And it's exactly the same pattern, just that, well, we used a slightly more refined structure. Okay. So, of course, this is not the only place where this simple aggregation and replace it by weighting has been applied. For instance, there are the squeeze excitation networks. And in this case, you go and weigh by channel, right? So you have overall, you have filters in your, ConvNet, and then you use the overall state of your attributes to come up with per channel weightings. You rescale those, and then you propagate it further. And it turns out that these SE nets, as they're called, work a little bit better than their non-excited networks. And yeah, it's actually a very cheap modification. Now you can do the same thing for graphs. So rather than in a graph network where you just take your neighbors, rather than just pooling over them, you can do attention pooling. And guess what? It works better. Which actually makes a lot of sense, because let's say I'm following maybe Obama and I'm following maybe, I don't know, Justin Bieber. Then, well, okay, I don't follow Justin Bieber, but just suppose I do, and then I follow some other random person. Then it's a reasonable assumption to make that the tweets of different people who I follow might have different weight. And so what I can do then is I can use that to weigh and assess appropriately, which part is relevant, which part matters, and this gives me higher accuracy. Okay. So to make a very, very, very long story short, what we have is we have this thing called pooling, where you go and sum over the embeddings. And what you can do is you can use attention pooling to weigh and rebalance things such that rather than taking the original embeddings, you now take weighted embeddings and you aggregate those. Now, this query can depend on the context. I can possibly learn some function W that will help me do this, and then I just sum things up, and there we go. Now, there are a number of possible choices that I can use for this attention function. So one of them I'm showing here, so that's just, inner product between some embedding of X and some weight vector W. And yeah. Now, one of the reasons why you might want to use tang is because it kind of constrains the range, so the values don't diverge by too much. You can use that. So to sum things up, the simple version of attention is just go forth and replace wherever in your paper or your network you have pooling by weighted pooling, learn the weighting function, and your network will probably work better. It might be a little bit slower, but it will be a lot better. The other nice thing in doing that is that you're now no longer susceptible to the number of inputs that you have, right? So if you look at the set kernel, let's go back to this here, right? So in that formulation over here, we had to be careful of how to rescale things if the number of inputs was different. You could go and just say, well, I'm going to replace the sum by an average, which is perfectly reasonable. But effectively, you had to at least make some additional precautions to ensure that things are properly scaled. On the other hand, if I use this weighted averaging, then I can allow my model to focus on the relevant pieces, and I can allow it to process a variable amount of input quite easily. So this overall is actually a really important property of attention, that it allows you to deal with variable-sized inputs and to, for instance, come up with some estimate on them, or to process those elements in a set, as we'll see later on when we look at machine translation, or when we look at pointer networks and other things where we basically go and generate and emit symbols one at a time. Okay. Are there any questions so far? Yes. Okay, so I was asked to reshare the link to the slides. Okay, that's it. Yeah. If you wait until after the presentation, we'll have the slides with the updated version of references. It's just turned out that the network's a little bit slow. Okay, so. Okay, any other questions? Yes.
Could you just discuss or say you're going to aspects of kind of differentiating and exploring the attention function in the training process? Do you want to like organize your training epics in a certain way and best practices like that?
Okay, so that depends. Okay, so how to best train? Well, one thing that you may want to do is use a nice imperative framework where you, so in other words, TensorFlow Eager or PyTorch or MXNet Gluon, to write out a nice forward pass, because otherwise you're essentially at the mercy of whether somebody implemented that operator or not. That's the first thing. You may want to make sure that you don't overweight individual observations initially by too much. So you could, for instance, first train with attention switched off and then you turn on attention. There's a number of things. We'll get to that later, but overall it turns out to be reasonably robust. We'll see actually considerably more complex models as we go along. So for instance, in the case of transformers, you have multiple attention heads in a fairly complicated setting. So a lot of the considerations there in simplified manner apply to how to train basic attention networks too. One thing that you may want to do is, and we'll point to that later, so if you go to d2l.ai, you'll actually see a number of tutorials and notebooks, and I apologize for doing a bit of a bait and switch on you. We won't have enough time to cover the notebooks in addition to all the material, but if you go there, you'll be able to download all the notebooks and more detailed discussion as you go along. Okay, let's just go there. Okay. Any other questions? Okay. Yes, sorry.
So on this slide, phi is just some nonlinear function, right?
Yes.
So the class of these functions, why is it different from the class of functions like alpha times phi?
Okay. Oh, thanks for asking this. So phi of x is just some embedding of x, right? And this could be pre-trained, so it might fall off a truck like using a BERT embedding or a Word2Vec or whatever. You might use that for, for instance, you can have a pre-trained model for images, maybe your favorite ResNet 50, pre-trained on ImageNet or DarkNet or whatever. Alpha is a scalar. Now, phi of x only really depends on x. Alpha, and I'm playing a little bit fast and loose with the notation here. Alpha is a scalar. At least right now, it's just a simple number. Later on, when we look at transformers, it'll be actually a low-dimensional vector. And that's set up in such a way that it's normalized. So technically speaking, I would have to provide alpha not just with lowercase x and w, but also with capital X in order to make sure that we have the proper normalization. So if you look at the last line, you can see what's going on. Alpha of x is proportional to e to the w transposed tang of ux, and then you normalize. Okay. I think the gentleman behind you also has a question.
Yeah, Yeah, so this is a very nice way of looking at self-attention, writing that.
They give it like...
Is it based on the problem? Indeed. The issue, though, is that, as said, if you need a large number of steps, that would be only required for fairly complex queries, where you need to take many logical steps in order to get somewhere. In that case, I would strongly recommend that you use something smarter than just simple iterative reasoning. You might actually want to structure and shape how your attention behaves, right? So you might, if you need multiple steps, you probably want to include some prior knowledge on your problem, right? This could be a fun paper. So for instance, if you know that first you need to identify the people in the image, and then you need to find out what they're doing, and then you can count how many times they're doing certain things, then it's probably a really good idea to encode that in the structure of your problem. Because otherwise you are going to need a lot of prior knowledge, or you're going to need a lot of data to make this work. Okay.
Could you go back 2 slides where you are answering the questions? Yeah, so the first image on the left top, so it's actually seems to be cows or bullocks or whatever.
But I agree, but it just turns out that both the labels and the prediction are horses. I also would have thought these are cows, but I don't know. I guess.
So
yeah.
So my question is, how did it infer it's cow? Means horses? Means what did you provide it to train?
So what? So these results look actually more impressive than they are. Anybody who's done VQA knows that in a lot of those data sets, you have a set of possible candidate answers. And so the candidate answers might be something like horses, laptops, trucks, cows, and fish, right? And then that very quickly narrows it down that there can only be a small number of things. So that significantly simplifies the problem to something that's a lot less impressive than just this directly looks like. But yeah, that's pretty much what all VQA and also a lot of the text understanding problems do. Part of that is that otherwise it's just really hard to measure whether the answer is correct. Because, if the network might answer white horses and the answer is horses, then you need a human to identify and say, well, actually white horses is really good, right? So some of it has to do with the imperfection in how people design training sets. Nonetheless, if you feel compelled to do so, I would strongly encourage you to help generate better training sets. Okay. Yes, question in the middle.
So when I think about attention, I think it depends on the task. If I'm driving and I'm hungry, I'm probably going to pay attention to restaurants, but if I'm doing something else, I'll pay attention to other things. Mm-hmm. So how is it possible that these simple functions are repeatable across that? So why does this formulation actually make sense in terms of attention?
Okay.
And obviously, when you do it recursive, the answer of 3 layers is good because otherwise it's not satisfactory. So what are the foundations of this? Why does it make sense to do all this?
Okay. This is a good question. And first of all, the unfortunate answer is that even for the simple attention mechanism, that one is still not really well analyzed, and I have some open questions at the end. So basically, if even proving something like consistency for a simple attention mechanism would be nice if somebody could do that. But okay, to answer your question, why does it work? Well, what happens is that you're basically also learning an embedding of the query, right? And you're not just taking the query and you don't have any other context, but you're going to use a lot of text to come up with good embeddings for the text and thus the query. You're also using a lot of context and thus prior knowledge to come up with the embeddings for the images, right, for the objects. Maybe you'll even use an object detector and a few other things. So therefore, you're really standing on the shoulders of giants, at least data-wise, in terms of transfer learning. So those give you good priors on what the relevant representations ought to be. And that will help you do well for certain applications. So for instance, if one of the questions was, what is the amount of pixel noise in an image, then probably a ResNet embedding that's trained on ImageNet will not do very well, right? Because it's actually trained to ignore this or to also ignore other stylistic variations, right? So to some extent, the reason that this works is because a lot of the, well, let's say deep learning benchmarks and problems are actually quite related. They focus very much on the types of questions that humans pose, or also in some cases it's just that a data set gets released, it's available under some beneficial license, and then different teams pack on different labelings on top of that. So for instance, if you look at the MS COCO data set, there are various extensions of that all rely on the same data set. That's to some extent because humans tend to be lazy, right? So if you already have a data set available, that's awesome. So I don't have to do any extra work to add another set of labels to that. I don't have to fight with my legal department to get approval for releasing the data set because somebody else already, ate the frog before you, right? And that's part of the reasons why a lot of data sets are related, and that sometimes may make you think that our networks are smarter than they actually are. Okay, there was a question over there on the right, and then we can maybe move on.
Hi. So most of the cases we have seen the key and the values are the same set of vectors. So in the original transformer paper, when they have multiple heads, they project these keys and the values to different subspaces. And they say that different head looked into different semantic meanings. That's why they do it. My question is, when we have one head or one kind of attention, what is the necessity of doing this extra projection on the key and the value vectors?
So by default, start with keys and values being the same. Only if that doesn't work, use different things. To some extent, it is a function of what the experimenter needs to do. Like in the very first example that I showed, the Watson-Adara estimator, it's very clear that the key are the x's and the y's are the values, right? Because you want to regress, and you only care about the x's insofar as they tell you, how close to your query they are, right? So I would, unless it feels natural to do so, equate key and value. And that's actually what a lot of modern approaches use. It's just that, well, be aware of the fact that you have a choice to use different things.
Sure. Thanks.
Or you might have additional values available that you shouldn't use otherwise. Okay. I think we need, okay, well, one last question and then we need to move on.
Are there some common techniques to make multi-layer attention network train easier? So do you typically train them end-to-end, or say train the first layer first and then and add another layer and then add the third layer?
Okay, so again, it depends a little bit. So first of all, if you have a problem that's applied to a common data type, and in almost all cases you would have that, like you would have text or you would have images or audio, whatever, then by all means use a pre-trained network that you get from there to apply it and use it. This works most of the times. Let me give you an example where this doesn't work. So let's say you want to have an image search application where you want to look up satellite images. And if you want to do that, you might think that, well, okay, satellite images are images after all, and let's say they're actually RGB. So let's just pre-train some embeddings based on ImageNet and then use them for nearest neighbor lookup for satellite images. And we did this, and it was a total disaster. It didn't work. And part of the reason why it didn't work is because satellite images look very different from other real images. So in the end, what we had to do is we had to pre-train on OpenStreetMaps, and then things were fine again. But this is about the only example that I know where pre-training actually did not work at all. In most other cases, pre-training and learning embeddings for the specific types is your friend. And we'll actually get to this in much more detail later on when we discuss BERT, and we'll see how you can use that to solve a wide range of specific applications for NLP with BERT as pre-training, and you get better outcomes. Okay, so now let's move on to something very logical. Namely, so far, we iterated over the input with a query, and we got a single output, right? So obviously, rather than having a single output, you could have multiple outputs. So let me motivate this. Suppose I want to do sequence to sequence, for machine translation. And this is this paper from 2014 that was quite, let's just say, a remarkable presentation at NIPS, because the entire presentation was something like, hey, we took an LSTM, many stacks, and we trained it on many machines, and it worked. Right. So what did they do? Well, they basically went, so this is Sutskever, Vinyals, and Le. They took an input sequence, and they ran it through an LSTM, and they got some embedding out of it, so phi of S. And then they applied this on a decoder, and in the decoder they, generated, the target language out of that. So I input A, B, C, and then I get phi of this string, so basically some representation, and then I start, generating W, X, Y, Z in an end of string. And of course, after I've generated W, I use that as an additional input to generate X, and then to Y, and so on and so on. Okay. And this works beautifully if I have very short sequences, like the table is round. Well, it's not great poetry, that is just thrown fine. But it started failing quite badly when you had very, very long sentences, maybe with sub-sentences. So German is really infamous for that, where you might have sentences that span 20, 30 words, and it's actually considered great style if you craft those properly in English it's considered bad style, but in German people think that you're very smart and educated if you make really complicated sentences. So, unfortunately, this sequence approach fails miserably for that, right? And there's a simple reason, because, well, the representation isn't rich enough for those really complicated 20 words and more German sentences, right? Overall, you're just asking the network to do too much to embed a very, very long sequence into a finite dimensional state vector, and then to disgorge that in the target language. Right? You're basically forcing that poor network to memorize that source sequence and then to translate, and keep in mind all the things that it's already generated in the target, right? So try that for yourself with a very long source sentence, and you'd run into trouble. But if you think about it, this is actually making life way too hard for, that network, right? Because you actually still have your entire source sentence at your disposal. So, why not look it up, right? And what we can do is we can compare as we generate, the target sequence. As we generate one word after the other, we can look at, well, which ones have we already looked at, which ones haven't we seen yet? And, well, the hope is that this works better. As a matter of fact, this is the, grandfather of all the attention papers, really, by Badanocho and Benjo from 2014. And all those simplifications happened later, right? I mean, bar the Watson-Adaria estimator and probably a few statistics tricks in between. And then there's a variant of that by Pham, Dong, and Manning. And essentially, here's how it works. Right? So, you go and encode your source sequence as you would. And then you get some hidden state. And you use that hidden state to emit, let's say, X. Now what you do is you use X and, the current hidden state to look at a new attention weighting over your source. And then you emit Y, and then you figure out, what to attend to next. And you keep on doing this until you're through the string. The benefit is that now all of a sudden your hidden state needs to encode only very little. Namely, it needs to encode kind of what we've already seen so far and what comes next. It doesn't have to encode anymore what needs to be translated, but just like where in that process of translation we are so far. This is a lot easier. So, for instance, you can have now an attention weight, and this is now, clocked by, where we are in that sequence. And it depends on the embedding, and in this case, again, key and value are the same. And then I'm using the hidden state that I've also used to generate the output as the query for, what to attend to next. I then perform appropriate attention pooling, so I get those CIs back. I use that in conjunction with, whatever I generated before to come up with a new hidden state, and I also emit the corresponding YI. There are lots of different flavors of this, and every one of those works a little bit better and a bit differently, but the gist of it is that you use the hidden state to help attend to your source sequence, and then emit one target word at a time. So to show you this in a different graph that's a little bit simplified, you basically have the original source. This is encoded. You then use attention to query the corresponding key value pairs to generate an output, and you do that one at a time. And then you do clever things like, fancy beam search and whatever to get on with that. So, if you will, this is one beyond memory networks, because memory networks, do this maybe 1, 2, 3 steps, and then they emit one symbol. In machine translation with attention, you emit many symbols, one symbol at a time. So to show you that this works, well, this is basically what happens if you look at blur scores, so larger is better for different sentence lengths. And it turns out that if you use attention, then the system doesn't degrade with longer sentences, whereas if you don't use attention, then, well, it does degrade. So this is essentially the even slightly more complicated version of iterative reasoning. Before that, we just took multiple steps and then we generated one output. Now we take multiple steps, and at every step on the way, we generate one output. Okay. So we've taken quite a long journey from pooling to weighted pooling, to weighted iterative pooling, to weighted iterative pooling where we emit one symbol at a time. Okay, and now it's time for me to shut up and hand over to Aston, who is going to be your host for the rest of today.
Thanks, Alex. So as Alex just mentioned, we have been on a very long journey until we can do the iterative pooling, attention pooling, while we emit the symbol at each time step. And actually, there are many other applications which also inherit the same spirit. So for instance, pointer network is one important candidate. And this can be used to solve some famous algorithmic problems like convex hull. So recall that a convex hull is to find the smallest convex set to enclose the input like this. So for instance, if you look at the input, which are 4 points, with each has 2 coordinates, then the output will be the parse to enclose such data points from the input set. Like we start from point 1, point 4, point 2, point 1, back, then it forms a smallest convex set. So at the first sight, it may be tempting to formulate this problem with sequence-to-sequence model. However, recall that in sequence-to-sequence model, for instance, for those that we use to solve the machine translation problem, the output size is usually predefined. For instance, the output size in a machine translation problem, the output size is the same as the vocabulary size of the target language, right? But for this problem, the output is only determined by the size of the input, because at each of the decoding stage, the output should be one of the elements from the input set. So how can we solve this problem? Then we can still use the sequence-to-sequence idea. For instance, here we can use two recurrent neural networks to encode and decode. The encoding will be using an RN to encode the input set, like the left part of the paradigm. And then at the decoding time, at each time, we will use the current decoding hidden state as a query to pull over all the inputs from the input set. And the elements of the input set will serve as both a key and a value. Like in this case, the hidden state of the decoder will be the query, and then we use that to pull over the inputs from the encoder, and we can directly generate the prediction distribution by using the attention weight when we apply the attention here. And note that here, every time, at each time step of decoding, the output from the previous time step will be fed into the next hidden state computation. So that's why, in spirit, it is still the same. It's very similar to the machine translation problem, where we will use the iterative output as the input for decoding the next output by using attention. So in this case, you can see that for the purple color, at the first time step of the decoding, we pull over all the hidden states from the encoder, and then we output the 1 as the output for this time step, because the distribution weight may be the highest over the distribution. Then we send the input, the output generated output 1 to the next hidden state to decode the next output. Then we do it recursively. So besides the convex hull, actually such pointer networks can also solve other similar problems that, like the Delaunay triangulation and the traveling salesperson problem, which is actually NP hard, right? So we just can use the deep learning like with attention and the iterative output to solve such algorithmic problems. But now it's already 2019, so we saw that originally they used 2 RNs for the encoding and decoding, right? So now there are some very simple enhancement for the existing original model. For instance, one way is that we can apply the transformer to encode the inputs and also maybe the output as well, which we'll cover later. And also we may use like graph neural networks to encode more information from the graph representation perspective. For instance, like the traveling salesperson problem, right? We have distance between each data points. So this is essentially a graph, and maybe for the graph neural networks, this is a very good background for such a powerful graph-based model. Okay, so another example that inherits the same spirit is the neural Turing machine. So for an NTM, the controller network will take the input from the environment, then generate the output. And before generating the output, it has to try to pull over from the memory cell. So the memory cells actually form a memory bank here. And every time it will read from the memory, like read some certain heads from the memory cells, and also write back to the memory bank. So the memory cells that written back is the generated output that will be used for the pooling later. So here, the values in the attention mechanisms are all the memory cells, and the attention weight here will be applied to pull over the memory cells in order to generate the heads for decoding. So different from many other models or networks. So in the neural Turing machines, the attention weights actually are stateful. So it means that explicitly we use the attention weights from the previous time step in order to obtain the attention weight of the current time steps. So this is like an explicit make it stateful, that we always leverage the information from the previous attention weights to obtain or update the current attention weights iteratively. And also for values, yes, it is also stateful. So as the concrete example, so the NTM actually is compared with LSTM on copying a sequence. Although we know that LSTM is proposed to handle the gradient validation problems, right? But it actually doesn't perform very well to copy a sequence when the sequence gets very long. For instance, in this experiment, when the input sequence is longer than 20 tokens, then LSTM systematically fails to copy such a long sequence. So yeah, you can see that 30, 50, or even 120, LSTM doesn't copy cannot be trained to generalize the sequence copying. However, with the neural Turing machine that also incorporate the attention mechanisms, it performs much better when the sequence gets longer. Although, when the sequence gets too long, like 120, there's one global error there, where after that decoding time step, which is pointed by the red arrow, you see that it pushed all the subsequent vectors one step back. So it means that every vector from the t-1 is copied to time step t at the decoding time. So this also causes a global error. So this is also shows the limitation for the NTM. Okay. So then in the rest of the tutorial, then we will cover the more powerful mechanisms, which is using multiple head to design our attention algorithms. So multi-head attention was proposed 2 years ago by Vaswani et al. That it will project the input query, key, and value into multiple different subspaces before concatenating them together. So for this one, you can see that for the key, query, and value, we use different parameters to perform the linear transformation in order to get their representation in multiple different subspaces. So you can see that we have a dense layer, right? So the dense layer is the same as the fully connected layer, which is perform the linear transformation with its own parameters. Then we concatenate them together to formulate the multi-head attention. So the transformer is purely based on such a multi-head attention. And actually, transformer has been the key to advancing a lot of state-of-the-art in multiple different problems, which we'll cover later. So to provide some more concrete context about transformer, it has two parts, two key components. One is the encoder, the other is the decoder. So for encoder, we see that the input sequence can be passed into an embedding, and also together with the positional embedding to formulate the input of the transformer encoder inputs representation. Then we use their key, query, and value from the same representation to fit into the multi-head attention. And then by adding the residual connection with the layer normalization, we obtain the new representation to fit into the next two-layer, multi-layer perceptron with the ReLU activation, which is the position-wise FFN here. And we apply the same residual network, residual connection, and the layer normalization to obtain the output of one single transformer encoder block. So this is how we represent the input sequence with such multi-head attention. And note that because all the query, key, and value in this encoder come from the same input tokens in the input sequence, we also call it self-attention. So it means that all the query, key, value are the same. Then for the decoder, there are actually two important sources. So one is what we have described just now, which is the input representation from the transformer encoder. The other is the representation of the generated outputs before the current time steps. So for instance, think about that at time step t, we want to encode or represent all the generated outputs before time step t. Then we can still apply such self-attention which is similar to that in the transformer encoder to apply the self-attention with multiple heads and to get the representation for each token of the generated output sequence. But there's one important difference between the self-attention in decoder. That is, in the encoder, actually for each token, it can attend to tokens of all the time steps. However, in the decoder, for each generated token, it can only attend to the tokens that are no later than the current time step. This is because we cannot simply use the future information to decode the current token. So that's why this self-attention is we have to apply some mask matrix to hide the attention links to prevent predicting using the future information. After that, then we use another multi-head attention to decode the output, where the query comes from the representation from the previous time steps of the decoder. And the key and value all come from the input representation from the transformer encoder. Then the rest will be very similar to the transformer encoder that we apply the normalization and also the residual connections. Then we apply another dense layer to output the decoded token. So this is the transformer encoder and the decoder part to enable us to apply it into the machine translation problems to perform the sequence transduction. Right. And actually, the multi-head attention can also be used in many other problems, for instance, in computer vision. So in semantic segmentation, the task is to classify a certain pixel of an image to recognize what type of this pixel is to provide some more semantic meaning. So for instance, if you only look at this partial image, right, and let's answer, if we want to answer the question whether this certain pixel is a sea or a water, it can be ambiguous because we don't know whether even for human beings, it's very hard to tell whether it's a sea or water, right? And if you have more information about the picture, for instance, when you see there's a boat here, you probably tend to classify those pixels, the surrounding pixels at the bottom, as sea rather than water to be more specific. So actually, multi-head attention can be used to pull such feature representation like the boat in order to help infer the semantic meaning of the pixels, which are even more distant from the interesting objects like a boat here. So this is the mechanisms proposed by Zhang et al. This year to apply the multi-head attention for semantic segmentation. So first of all, for the raw image, we still need to use a backbone network like a ResNet 50 to obtain the feature map. So this is like a feature extraction from the raw image. Then after that, we can project such a feature map into different outputs like the key, query, and value. Then at the prediction time, we can apply the multi-head attention to use the query to pull over the key and together with the value in order to determine whether we need to allocate some attention or the alignment bias over different feature representation, which is from the backbone networks. For instance, maybe some certain patterns may formulate the representation for a boat. Then we can allocate more attention to that in order to categorize the surrounding areas to be sea. So as a concrete example for the performance of such a mechanism, you can tell that for the original fully convolutional neural networks, this actually fails to recognize the surrounding areas for the boat to be sea. Actually, you see that there's multiple area on the left bottom. It classifies them to be water rather than sea. And if you apply the multi-head attention to pull over the feature map to have more information about what's around, then the model can be smarter and more specific to categorize certain elements or the pixels to be specifically to be sea rather than just water, by allocating more attention to those feature representation of the boat. Okay, so next we will talk about some more powerful pre-training methods that is coming from the transformer. So before that, I can take some questions if you have. So any questions so far? Okay, so let's move on to the pre-training part. So,
I have a question.
Oh, yeah. Sorry, I didn't see that. Yeah.
Have you looked, do you know if there's any work that has looked into the weights that the transformer learns? Like, for example, in different layers, you have different distribution of the weights or things like that?
Sorry, can you speak a bit louder? It's a bit distant.
Okay.
Yeah.
So are you aware of any prior work that has looked into the weights that the transformer learns in different layers? So they have, I think, 6 layers in the original paper. Has anyone looked into those, like, sort of qualitative things?
Mm-hmm. So I noticed one paper that actually tried to understand what the transformer learned from NLP tasks. Actually, the take-home message is that the hierarchy information that we would have expected are not that obvious. So this is the take-home message for that paper. Yep, questions?
So if we look at the output of neural Turing machines, it's pretty interpretable in the sense that if you see the output that is generated for copying, you see that the machine actually takes the head to the first part of the tape and then copies it. Depending on the task, you can make sense that it's kind of creating a program in itself, right, for executing that task. Now, if we look at the pointer networks paper, is there some kind of intuition that could be associated with, say, the instance of pointer network which is meant for convex hulls? Or some other task. I personally tried implementing sorting through pointer networks, and it worked fabulously for the sequence lengths on which I trained it on, but the performance rapidly degraded the moment the sequence length. It was shown a sequence which was not of the same length as what it has seen in the training data. And I was trying to figure out what's going on there, and I don't have a clear interpretation of what the encoder and decoder and the attention are actually, what is it that they're trying to represent internally in case of pointer networks. So any insights that you might have would be grateful.
So for the pointer networks, so I think my insight is that at each decoding part, it may try to make use of all the existing generated outputs to help determine which will be my next input from the predefined input set. And the sorting, for instance, for the sorting part, I think if you have a very small data set, it may have the potential to overfit rather than generalize with certain patterns. So although I haven't experimented such results, but my guess is that when you try training on very large data sets, it may have potential to generalize better than the risk of overfitting of the input of the provided inputs.
Would it be correct to say that in case of sorting task, after it has generated, say, first 3 outputs of the sequence, at the next point of time, it is actually trying to emulate comparing the latest output with all the inputs in a subtraction or addition, primarily subtraction sense, and trying to figure out which are negative, which are positive, and take the smallest one and try to output that? Or is that interpretation very naive and it's some kind of embedding that it is learning which cannot be really that easily interpreted?
Yeah, that's a good point. So if you look at the output generated from the pointer network, right, even actually for instance, like the traveling salesman problem here, the output is actually not correct. So that's why my thought is that on smaller data set, that definitely has a potential to overfit to memorize how to do the permutation of the input data points. But when you generalize, it may have the chance to make use of more information from the input. For instance, the distance between each data point here, to understand how I just permutate all the data inputs. So that's why here we say that maybe we can also make use of the rich information from the graph. And that may possibly provide with us more insights of what we learned to do the permutation. Because if you look, if the model can look at what the labels of the graph in order to decode, then maybe it can provide more insight and make it more interpretable, which is also not done by these original pointer networks.
Thank you.
Okay. So let me move on to the pre-training. This is actually a pretty exciting topic, especially in the past year. So past year, I think this is many of the breakthroughs in NLP come from the pre-training schemes. So now let's look at this. So among this, BERT got pretty impressive because it achieved state-of-the-art on 11 NLP tasks, and it's built based on the encoder representation from the transformer. So how it works? So to provide more context about the pre-training, so for instance, recall that for the computer vision, right, we can pre-train like a backbone networks based on the ImageNet or even larger data set to obtain the multi-layer representations of multiple levels of abstraction for the input image. Then for NLP, we can also do the same. We can actually do the pre-training on the corpus to learn the representation of the sentences in the text corpus. Then we can fine-tune such representation from the deep pre-trained layers to solve some downstream NLP tasks. So this is what the pre-training can work in NLP. So like in this case, we can add just one or more output layers for each new task to do to transform the pre-trained language representation into the output of a specific task. So like in this example, which is probably the simplest case, we can use the pre-trained word embedding like word to vec or glove or fast text to obtain the token representation. And then if we want to obtain the representation for the entire language, we can simply sum it up, right? However, this ignores the sequential information entirely. And how to encode the sequential information to have more context? So like a simple thought is to use the language model, right? So which is factorized based on the autoregression. So GPT exactly does this by using the transformer decoder based on the multi-head attention. And it pre-trained the language model on the full-length documents with 12 blocks and 12 heads. So each block is a transformer encoder block that we have covered before. But different from, so there's one thing that we can highlight, which is that GPT trains on the full-length documents. And this is very different from BERT. BERT only pre-trains on sentences or like a pair of sentences. So this is one difference. And it also achieved the state-of-the-art results at that time. However, there's limitation for the language model representation. So like, if we want to obtain, so like, let's look at the examples at the bottom. The highlighted word bank, how do we obtain the token representation for bank? If we use language model and we go one directional, it will only look at the previous tokens to understand the context in order to obtain the representation for this token bank. However, if we ignore the context which is after the word bank, it actually misses a lot of useful information to obtain a more accurate representation for the word bank in this context. So that's why, in order to understand or represent language, bidirectional context will be very useful. So this is what BERT does. It is based on a bidirectional transformer encoder to represent the language. And it's a very big transformer encoder that is pre-trained on books and Wikipedia, which have more than 3 billion words. And you can see that the parameters, they have two versions. So the larger version have like 340 megabyte parameters. So now, with such bidirectional encoding, how do we really represent the input language? Actually, as I just mentioned, BERT is pre-trained on sentence or a pair of sentences. So let's look at a pair of sentences. For a pair of sentences, first of all, we try to obtain the token embedding for each word in the two sentences, and we place a spatial token called SEP to separate these two sentences in such a pair. And we also add the segment embedding, which is the same for the same sentence. So in this case, you can see that in two different sentences, we have two different segment embeddings to be learned in order to distinguish the two sentences in a pair. And also we have a beginning of sentence a token, special token, in order to try to represent the entire sentence or the entire sentence pair for decoding to the downstream NLP tasks. So if we have only one sentence, actually we can just ignore the second sentence. So it means that the one sentence representation is just a subset of a pair of sentence representation. So then we have two different tasks to pre-train such a BERT model. So one is the mask language model, where we look at both of the context of the word to be predicted. So you can see that it's very different from the language model that we look at only the tokens from the previous time steps. So in order to do that, we randomly mask 15% of all the tokens to be predicted. And we can, and there are, for 80% of them, we just replace it with a special token called mask. So it means that we use the input sequence is like the context information together with the mask, which does not have any meaning to predict the mask token. So it forces the prediction to use the context information from the two directions in this case. And in order to help the model to bias towards the correct prediction, for 10% of them, it will cheat by using the true answer, which is the actual token. So this is like cheating, right? We use the token to predict the token. So, but it only takes 10% of time in order to bias towards the correct prediction. And then for the rest, 10% of time, we just replace with the random token to add some noise like a regularization. Right. So another task is to try to learn the logical coherence between the sentences of a pair. So like in 50% of time, we just replace the correct next sentence to be a random sentence and give such pair as a label called a negative. And then for the other half, we just preserve the sequential pair of sentences to provide and label it as true. So this is like so it means that we have we can try to learn the relationship between a pair of sentences with such labels. And in this time, you can see that both of the tasks, they are purely from the unsupervised large corpus. So although in every time for the mass language model, we do have the ground truth for the predicted token, but this is from the corpus, right? So we don't need to manually label it. And also for the next sentence prediction, we also make use of the huge amount of corpus, like whether two sentences are a pair or not, or like whether they are sequential or not. So this, we don't need, in order to achieve this, we don't need to manually label such two sentences to be whether they are a pair or not. So this really leverages the power of the unsupervised corpus without any labeling cost. So then, once we have such a pre-trained model, then we do obtain the representation for each token of the transformer encoder, and we can also fine-tune to different downstream tasks. So here are the details. So for sentence classification, we can use the very first spatial token, which is called the beginning of sequence, because it applies the attention over every token of every time steps. So it has the potential to encode all the information from the inputs, and we just use that special token to add to append another dense layer to transform it into the categories to perform the sentence classification. And in this case, we can just train the dense layer from scratch, or sometimes we can even like fine tune the weights in the pre-trained BERT. This is also, both ways are possible. So then in them entity recognition, we want to predict the label for each word in a sentence to be like the beginning of an entity or end of an entity, like location, person, or something, right? So in this case, we can retrieve the feature representation from the pre-trained BERT for each token. Then we can also just transform it into with the dense layer to the entity type. For question answering, we can. So question answering is that we use the question to answer. We want to output the beginning of the answer and end of the answer by marking the beginning and the end position of the story. So in this case, we can try to predict the beginning of the answer by marking each of the position of the story, and we can use a parameter s, which is s here, to be the parameter and perform the dot product between this parameter and all the feature representation from BERT for the story, and then we can perform softmax to get the highest to get the token with the highest likelihood to be the beginning of the answer or the end of the answer. So this is how we can fine-tune to question answering. So then GPT-2 gets even larger. So here you can see that it has stacked 48 blocks and which result in 1.5 billion parameters. But for GPT-2, it's larger than the GPT-1. So but different from BERT, it only used the decoder part of transformer. So here, notably, GPT-2 pre-trains on the 8 million web pages, and after training on such a large corpus, when they find that they don't need to fine-tune towards any specific language modeling data set to perform the language model task there. So it means that it achieved a zero-shot learning. You don't need to fine-tune anymore because the pre-trained result is already good enough. So here is a demo for GPT-2 because like previously, some people, they argue that it is the most dangerous. Oh, there's no projection? Oh, okay. Okay, it's fine. I can just skip this then, but if we have time, we can still do that. But don't worry, we can do a demo later. If you are interested, you can just come to the booth, come here, yeah. So, but this is like a backup plan, right? So once we provide the inputs, the prefix, like average human attention span is even shorter than that of a goldfish. Then you can see that the GPT-2 can keep generating the word, right? To keep composing the text, and it is partially readable, right? You can see that it's partially readable. So GPT-2 is pretty powerful in terms of the language modeling. So in the end, we still want to highlight the challenges for such powerful pre-trained models based on transformer, because as we just mentioned, they have a lot of the parameters which may make it very hard to be deployed on certain resource-constrained devices like mobile devices or edge devices. So recently, there are a lot of work to try to make the multi-head attention or the general attention to be more structured, sparser, and even more light-weighted. So here are a few approaches to that. So recall that the heavy parameterization comes from the linear transformation of the key, query, and value in the multi-head attention. So we use the dense layer heavily in transformer architecture. Right? So what if we can just use a more lightweighted version of the fully connected layer or the dense layer. So one interesting idea is to apply the algebra of hyper-complex numbers rather than just the real value numbers. So that is and that will result in a quaternion transformer. Actually, we found that this can save the parameters immediately by up to 75% without significant degrading of the performance. And here's how we can apply this idea. So recall that in quaternion, it's a 4-directional hypercompact number. Then the algebra of the hypercompact number, which is the Hamilton product. This is the algebra for performing the multiplication, which is a Hamilton product of 2 quaternions. You can see that when we rewrite in a matrix multiplication way, all the parameters on the left-hand block, which is the matrix 4x4 matrix, the degree of freedom is only 4 rather than 16. But you can see that the permutation of the signed W is predetermined by the algebra of the Hamilton product. So on the right-hand side of the figure, you can see that if we apply the fully connected transformation by using the quaternion multiplication, we can just reuse these 4 parameters, right, in different permutation and with different signs to formulate the connections, the 4x4 connections. And because the degree of freedom is only 4, so the parameters is saved up to 75%. So this is a very simple idea. Then recall that the computational cost over a long sequence is also very high. It's because we perform the matrix multiplication in the attention computation, which is the softmax of the multiplication of query and the transpose of the key. Then we multiply by another matrix, which is a value. So the matrix multiplication has a time complexity of which is quadratic in terms of the input sequence or the output sequence. So when sequence length is longer, then the quadratic complexity is really, really terrible. So that's why you can see that even in BERT, right, the predefined sequence length is 512. But in some problems, like especially for the question answering, when the story can be tens of thousands of tokens, then if you apply the BERT, then it's not very powerful because the sequence like tens of thousands, right? So it's very challenging. And that's why recent works offered some alternatives to tackle the challenge to represent the long sequences by using transformer. So one approach is to just segment this input sequence. For instance, we can just divide the input sequence into several different segments. And then we only train the transformer encoder or decoder just based on each segment. So it's like we train segment by segment. Then during the inference time, we can just output or decode a sequence, a token, by using the current segment. Then after that, we can just shift one position to make use of the new segment and predict the next token and perform the inference computation all from scratch. However, there are two drawbacks. So one is that the inference, right? The inference, every time you just you shift one position, you perform all the inference computation from scratch. So that's a lot of time capacity. And on the other hand, because for doing training, we segment the sequence. So this causes the context segmentation. So mean that we lose the context information from across the consecutive segments. So in order to do that, we probably can borrow the idea from what we have done for RN, right? Because recall that in the early times of RN language model, we also have similar problems. We cannot simply train the RN language model on a very long sequence. And instead, we use a truncated BPTT to perform the training. So this also, we can tweak the transformer, segmented transformer training as well by just caching and reusing the state from the previous segment to train, to every time we only train train over the using the gradient of the current segment, but we still cache and make use of the result from the previous segment to do the training. So this is also in spirit very similar to the idea of BBTT. And since this time the context information is able to flow across the consecutive segments, then during the testing we can just fill in a very long sequence and predict the tokens of different time steps all at one single pass. So in this way, it is a way to resolve the context fragmentation problem and also the inference acceleration during the inference time. And as another alternative, we can actually try to specify the attention connections. So recall that during the decoding time, like at the time step 5, you can only attend to the generated token at time step 1, 2, 3, 4, 5. But on the other hand, why should we always attend to all the generated tokens in the previous or the current time steps? So why not we specify such attention connections? So here, the sparse transformer offers such a way. So if you look at the middle figure, we can actually specify it by selectively attend to some certain previous time step token with a stride. So this stride offers a way to capture some periodic patterns possibly from an image or from certain types of music. And for text, if there's no lack of such a periodic pattern, we can just selectively sample some fixed position from the previous generated output. But the idea is still to specify the connections between among the attention connections. So, yep, before we move on to the next, so do we have any questions so far?
Hey, so in the transformer paper, one key piece seems to be the positional embeddings, which are used for representing temporal ordering. The paper is kind of light on details about how they came up with the sinusoid form for it, how important it is, and is there any room for improvement there? What are your thoughts?
Yes. So in the transformer paper, they use the sine cosine functions for the positional embedding, and actually and you also have the hyperparameters depending on the position to control the period of such a sine cosine periodic functions. So this actually offers different ways to view the positions at multiple different dimensions of the positional embedding. Actually, we have more details of the positional embedding in the d2l.ai link. So you probably can look at the section 9.3. We have the details there. Yep.
Hi, so I have a very basic question about the output size that we use in translation models. Like you said, that it is typically equal to the size of the embeddings, right? But can we reduce it to a much smaller set of words based on whatever the sentence is there? For example, if I want to translate, I'm going to the market. You know what these words are in some language like German. For every word, you can have a mapping. So instead of having to compute the probability of all the words in the German language, you could possibly reduce it to a much smaller set of words. Now I'm wondering, if we do this, will it lead to a significant reduction in the computational cost?
Actually, I will have a better idea than just try to predict over the raw vocabulary set. So the simple idea is to use the BPE, which is a byte pair encoding. So in this case, you probably can try to formulate the tokens based on the frequency or other heuristics. So in this way, it will give you an immediate benefit of reducing the size of the vocabulary, which can hopefully accelerate the computation. So the byte pairwise encoding. We also provide some context in d2l.ai. You can check that. Yep. Any more questions? Yeah. Okay. So then I'll pass on to my colleague Alex, so he may share more paper ideas with you. Okay, thanks.
So given that we're a little bit short on time, let me just quickly go through a couple of open questions and a bit more supplementary material, because the gentlemen who run the audio, they're actually here, they get paid for the time that they're here, so they need to be out of here by 6. So one, I think, very burning open question that we have, and any theorist here in the room who might be willing to tackle this, is the issue of function complexity. So we've seen that attention actually works really well, and with comparatively simple functions, we can actually model rather rich dependencies, and that's because you basically learn the mechanism. Now the problem is capturing and quantifying the function complexity is non-trivial. So for instance, if you look at iterated function systems, then even some very simple functions can give you, strange attractors and all of that. So analyzing this is probably going to be non-trivial. The other thing is, of course, how do you actually regularize those things? Do we need a specific mechanism to regularize attention? Also, the other thing is, how do we interpret things? And there's some very nice recent work that just came out, like in the past few weeks, one by Hewitt and Manning, and then one by Können et al., where they actually analyze things for BERT. And essentially what they do is they look at the attention weights, they embed parse trees, and then they regress from attention weight to parse trees, and then there's a little bit of reasoning which shows that an L2 embedding, and they call it like a distance squared embedding, but it's really the 2 norm that matters, that this is where things work quite nicely, which actually you would kind of expect that if you regress between 2 things that you'll get something. But I think more interesting is, can we actually use some ideas from NLP, for instance, to guide the steps within the reasoning, within the attention? Is there a structure that we can use? So to some extent, the sparse transformers paper takes a first step where they explicitly hack, one head that looks at the past k steps, and the other one that looks at steps every k steps into the past, and thus you can factorize things nicely. But can we do this a little bit more systematically? Because right now this is essentially, trial and error. Another issue is, for large state spaces, can we make them specialized? Can we have something that's, pseudo-random dense? Because quaternions are a really neat trick, and the fact that they work actually is a good pointer that there's something to be gained here, right? That rather than having, a full 4x4 matrix, you can parameterize it with a lower dimensional, just 4-dimensional space, and you still get most of the benefits. Can we do something with maybe pseudo-random dense matrices? Or maybe we can learn sparse structure. The other thing is, and this is probably the thing that would make a very significant breakthrough in terms of efficiency, can we use attention for power efficiency? So after all, this is part of the reason why animals use attention, right? Because if I'm looking forward and I'm looking at you guys, I'm not really paying attention to anything that's happening on the side, so my brain switches off the pieces on the side. Unless a saber-toothed tiger was going to attack me, in which case, lateral motion would kick in. But essentially, I'm saving energy by just focusing on giving this talk. Also, can we reduce memory footprint? Of course, there's the very low-hanging fruit, and this is essentially the parallel for all undergrads in your lab do. Take all the papers that haven't used attention transformers and BERT yet and rewrite them. And maybe you can get them published somewhere. So these are, I think, some of the open questions. I don't really necessarily have a good answer for all or any of them, but I think this might actually help. Now, a couple of resources. So Aston already mentioned this. So there's this book, D2L, and essentially, the 150 Jupyter notebooks, all open source. If you don't like something, send us a pull request on GitHub, and we'll incorporate it within hours. People are using it actually as textbook, and you can get the slides. If you have to teach a class in deep learning, just download the stuff and reuse it, and we're cool with anything. So there are Jupyter notebooks, and you can look at it on your mobile phone. Yeah, and of course there's open source. So if you go to GitHub and you don't like something, you send us a pull request. And you can kill trees and print it out. There's a class in Berkeley that we taught, 120 videos. And yeah, you have to listen to me, so please do something better on your own and put your own videos up. And so to conclude all of that, well, so there's actually a larger ecosystem of tools that sit behind this. So there's tools for computer vision, Gluon CV, Gluon TS, and Gluon NLP for computer vision, NLP, and time series, a deep learning compiler, TVM, then DGL, deep learning on graphs, and of course, underlying all of that MXNet. So if you liked what you saw, have a look there and enjoy. And thanks for coming along and, well, suffering through all of this. So thanks. And yeah, online there's references and other stuff, so you'll find all of that there. Okay, thanks.